Okay? You good? Okay, let's get started. So I'm going to talk about anomaly detection using the cortical learning algorithm. And this is something we, at Numenta, we really started doing in earnest sort of last year and started looking at a lot of data sets and applications for this. And in the beginning, we're interested in it. I thought it was, anomaly detection, kind of cool, detecting novel things in data. As we started getting more and more into it, I really started realizing how fundamental anomaly detection actually is. And we're living in a world where the number of sensors and the streams of data is just exploding exponentially. I mean, all of you, everyone here has seen those graphs of the Internet of Things graphs and all that stuff where the number of sensors is just increasing exponentially. And with so much data, there's no way to really sift through it all. And one of the most efficient tactics you could use is look to see what's different, what is unusual that's going on. And that's a very efficient way to parse through lots and lots of data. When you hear about the Internet of Things, people talk a lot about the data backbone behind it, but they don't really know what sort of analysis you should do on the data. And I've become very convinced that anomaly detection is one of the most fundamental things you want to do when you have tons and tons of streaming data, if not the most fundamental thing. So I think I've become really convinced that doing anomaly detection well in this new world of lots and lots of data is going to be really critical. And so hopefully with this talk, I'll try to explain a little bit what we've done. Just to give you a sense of the types of things that you could be using it for. One of the funnest Internet of Things devices I've seen is this one. This is the Mimo baby. How many of you here have kids or have had babies or are parents and so on? Okay. How many of you have been a baby at one point? Okay, so I think with this, most of you would be interested in this. So there's a company, I think it's called Rest Devices or something. It's a startup in Boston. They make this baby onesie with a number of sensors in it. So it senses the baby's respiration, it senses the baby's temperature, it senses the baby's movement, the heartbeat, and so on. And it streams this to your phone. So you have you have access to your baby's data. And what could be more important to a parent than doing anomaly detection on this data stream? If you have your baby and you want to know if something unusual is going on. So here's an example of something that, where anomaly detection could really play a very big role in this. On the other end of the scale, I did a little hack at Numenta last week where I looked at data from Bitly, and Bitly has an API where you can start clicking on things, and I started thinking, well, what is the web talking about? And you can start searching for all sorts of terms and see, what's unusual in the web today. So, I put it through our product, Grok, and this is showing the trace of people clicking on Lindsay Lohan web pages. And sure enough, our product detected an anomaly one day, and it shows the red at the bottom there. And when I started looking at what URLs led to that, she had, I think, declared that she had a miscarriage or something, and the web had gone crazy over this. So whether you want to save babies or follow the paparazzi, anomaly detection, I think, has a pretty lots of use cases. So anyway, so what I'm going to do is dive into some of the details of how we do it. There are basically three topics I want to talk about and cover today. One, what is anomaly detection? And I'll give you some more examples of anomaly detection. Then I want to go into a little bit of detail of how is the anomaly score computed in NuPIC and CLA today. The NuPIC code base does fundamentally prediction and anomaly detection, as Scott was talking about. So I'll describe at an algorithmic level a little bit what's going on there. And then the third thing, as most of you probably know, we released a product called Grok, which does anomaly detection on IT data streams. And I will explain how this anomaly score is used in the product Grok and what have we learned from actually trying to put out a commercial product that does anomaly detection. Okay, so those are the three things I'm going to try to cover today. And I have a little bit of sample code that I'll release as well as part of this, and maybe it'll make your life a little easier if you want to do anomaly detection today. Okay, so what is anomaly detection? So this is a definition from the dictionary. An anomaly is something that deviates from what is standard, normal, or expected. In our case, that something is a data stream and patterns. So this thing is, speaking of anomalies.
Even if it falls down, it works.
It works?
Yeah,
Can I just put it here?
No.
No, okay. I can hold it.
If it flops down, you can still hear it.
Yeah, I think my ear is
No, it's allowed.
not so, yeah, okay. Anyway. So that, yeah, so yeah, I think every time I turn here, it hits something. Inside my glasses. Maybe I'll do this. Here. Super. I'll be stuck. You'll have to hear from me for the. Okay. We'll figure it out. Okay. So in our case, this something is patterns. Patterns that are coming in over time, and you want to detect when the patterns have deviated from normal behavior. But there's a lot of subtlety behind the statement. So one example of the type of anomaly you might want to detect is a simple spatial or static anomaly. And this is the most common type of anomaly detection you'll find in the literature. And in fact, this is the most common type of anomaly detection used in the industry as well, where here I'm plotting two different sensory values, X and Y, and at any point in time, one of those dots is the reading of those two sensors. Okay, so spatial anomalies. So here's an example of the data, and it's falling into mostly two clusters. And you can see that there are 2 points there, 0, 1, and 01 and 02, that are definitely outside the cluster. So those will definitely be statically defined anomalies. And most of the people in the industry actually use something even simpler than this, which is thresholding. They'll say the value of X has to be less than this, or greater than this, or the value of Y has to be between this range. So essentially, these are like rectangles in this space. And that's what we see most commonly in the industry. So 01 and 02 would be anomalies. 03 is kind of interesting. It's got a few patterns in it, a few dots in it. Is that an anomaly or not? Well, maybe the first couple of times it is. After you see it enough times, it's not really an anomaly. It's rare, but it's not really novel as such. So, but nevertheless, this is kind of the one type of anomaly detection that you might want to do. Then there are temporal anomalies, and this is a data stream. I think it's an electrocardiogram, so it's basically heartbeats over time. And you can see that in the middle there, the heart didn't beat, and apparently this is indicative of arrhythmia or some condition, this type of thing. And this is interesting because the previous technique of looking at static values would not detect this anomaly. In fact, the values that are in red there are completely normal. They do occur quite often. It's just that they don't occur in this particular temporal sequence. Okay, that's what's novel here, is the temporal sequence. So that's another type of anomaly that you might want to detect. Okay, a little more complicated than the previous one. Here's a real-world example of this. This is data that we saw last year. This is the gear bearing temperature from a windmill. So you have all these windmills in windmill farm, and they have tons and tons of sensors, and they're spitting out data continuously. And what you can see on the extreme right is when the windmill actually broke down. You can see the temperature goes way up. But right there, the temperature actually starts behaving weirdly. It's a little subtle, but it's actually very indicative of the failure that happens later. So if you have a good temporal anomaly detector, you can actually detect the failure before it happens, just because you know that the measurements are behaving in a weird way. Again, any individual point in there is totally normal. It's the pattern over time that's abnormal. Okay. Then there are a couple other types that we've seen. You can have very random behavior, and you can have anomalies in that random behavior. So this is, we're working a lot with IT data. So this is data that's representative of latencies in your load balancer. So if you have a website and you hit your website, how long does it take before you get that page out? And most of the time it's really low, it's near zero. Some of the time it's near half a second. That was another anomaly. Most of the time it's there, and every once in a while, a few times a day, it jumps up to 2.5, 3 second range. This is completely unpredictable. You don't know when it's going to happen. It's random. Yet you can clearly tell that right there, there's something really unusual is going on. Your website is going a lot slower than it should be otherwise. And maybe a developer had pushed some code to it, or you changed the configuration of your system, or whatever. You don't know what it is, but suddenly the latencies have gone way up. And this is really hard. There's no real detectable pattern as such. It's just that the nature of the randomness has changed. Okay, so it's another type of anomaly that we see actually quite often in IT data and other types. Then there's another anomaly, which I'll call like a temporary anomaly. So this is a CPU usage, and you can see that on the left, it's sort of hovering between 6 and 7. It's noisy, but it's sort of staying in that range. And then there's a point in time when it suddenly spikes up. So that's an anomaly. Something unusual happens right there. And then, then it stabilizes at a higher level. Now, if you were using a pure threshold or some other system, you would definitely detect this anomaly, but then you would keep triggering an alert. However, in this case, this is once it stays there, and you can see the axis is on the order of days. Once it's there for a little while, it's the new normal. So it's not anomalous anymore. It's only anomalous at the point it shifted from one value to another. And once it stays there, it's no longer anomalous. Okay? So the regime here is now normal, even though the point here is abnormal. Okay? That makes sense? Okay, so there are a number of different kind of subtleties that you have to handle when you do anomaly detection. Okay, so just to recap, anomalies are, so we're defining as any significant deviation from normal behavior. Anomaly detection is extremely valuable in this area, and it's hard to do well. There are many flavors of anomaly detection, as I went over, spatial anomalies, temporal anomalies, changes in randomness, temporary stuff where you have to adjust to a new normal. So all of these kinds of things have to be handled. And one of the kind of hard things we also found is there aren't great data sets that capture all of these things in the industry. Maybe there are some we haven't found. There are some that capture individual things maybe, but it's not really, it's hard to find a good data set that really captures all of these things that we want to have. So that made it even harder to sort of evaluate how well you're doing and try to compare against other algorithms and so on. Okay, so that's anomaly detection. Let me talk a little bit about how the anomaly score is computed in NuPIC today. Okay, so NuPIC implements an anomaly score for streaming data sets, and Scott showed you programmatically how to do it, and we have example code for that. It's a core feature of the OPF, the Online Prediction Framework, and basically you just set inference type to temporal anomaly, and then it will output an anomaly score that is between 0 and 1 for every data point. Okay. NuPIC, it's implemented today, will detect a lot of the spatial and temporal anomalies that I showed you, and it does a pretty decent job at it. It's also, because the nature of the CLA, it's a continuously learning online system. So those temporary anomalies, it'll detect the anomaly, and then it'll quickly learn that that's the new normal. One of the really unusual things about the anomaly detection in NuPIC is that it can work for both numerical and categorical data. In fact, you can actually mix the two in the same data stream, and it'll still work just fine. And the reason for that is that we translate everything into this common representation, the sparse distributed representation, and then everything works on SDRs. And as long as you can convert it to an SDR, you can do anomaly detection on it with NuPIC. Okay, so this is a really nice property of the anomaly detection algorithm. Okay, so how do we actually compute the anomaly score? Here's a typical kind of OPF model. You have your data stream coming in, and you have a number of encoders that take that data and convert it into ones and zeros. And again, Scott showed you how to do that. Gets fed to a spatial pooler, then a temporal pooler, and then outcome predictions. Okay. And as you know, the CLA is constantly learning common spatial patterns in the spatial pooler, and it's constantly learning the common temporal sequences in the stream of inputs that are coming in. And that's done in the temporal pooler. And then at each time step, the temporal pooler is actually making multiple predictions about what might come next. Okay, so at every time step, it has an expectation of what's going to happen in the next time step. And it's not just a single expectation, it can actually branch. It can have multiple predictions of what might actually happen next. And then anomaly score is really simple. What we do is we look at the current value that's come in and see, okay, was it predicted at the previous time step, and how well was it predicted? If it was predicted really well, the anomaly score is 0. If it wasn't predicted at all, then the anomaly score is 1. And if the prediction is somewhere in between, then it's between 0 and 1. And the way this works is, if you're familiar with SDRs, is it works in column space. So the current input is represented in the OPF typically as a set of 40 columns that are on, and the temporal pooler is going to be predicting some number of columns to come on, and we just look at how many of the ones that were predicted actually, how many of the ones that are currently active are actually overlap with the predicted columns, and that's how we compute the score. Okay, so it'll be a number that'll go from 0 to 1 in increments of 1/40th, basically. Okay, any questions about that? Okay, let me give you a simple artificial example, and let's see if you get this. So here's a simple model of a sequence. So you start at A, and with 80% chance you go to B, 15% chance C, 5% chance D, and then no matter where you are here, you always go back to A. Okay, so here's a example temporal sequence. It's coming. Yes, PowerPoint does have this animation. I had to have at least one gratuitous animation in there. So let's say you have this sequence, and you've been learning on these statistics, and you're at A, and now you have some prediction about the next input that's coming in, and let's see what actually happens. So suppose B, C, or D occurs. Okay, what would the anomaly score be? Either B, C, or D. If any of these occur here, what do you guys think the anomaly score would be? Less than 1. It'll be 0 here, because if it's exactly B, C, and D, and assuming we've learned, everything's learned well and stuff, it'll be 0, because the temporal pooler will have predicted the union of these three to occur. Okay, so anomaly score will be 0. What if E occurs? Okay, 1. Any other guesses? So it's exactly. So it's generally going to be 1, but really it depends on how similar it is to B, C, and D. Okay, so if it's completely different from B, C, or D, it's going to be 1, and that's the most likely, particularly since this is kind of a trick question. I did it as alphabets instead of numbers. Yeah, very close to 1. But if these have semantic components to it, if they're similar to B, C, or D, then it'll be between 0 and 1, again, depending on and the similarity is in the column space. Okay. Okay, and then the next thing is, suppose A to E repeats quite often, multiple times in this scenario. Well, then anomaly score will drop to 0 again, regardless of how different it was from B, C, or D. Okay, so this is the continuous learning part of it. Simple example, but hopefully it gives you a flavor of, at each time step, what the thinking is. So here's an example. This is the same data set I showed earlier. This is the value, and then this is the anomaly score over time. And you can see that we're a continuously learning system. You start from the very beginning and you just go. So in the very beginning, the CLA does not really know how to predict. It doesn't know anything about the data. So anomaly score is going to be high in the beginning, because it's just everything is new at this point in time. And then it kind of settles down. Every once in a while, it'll go high because there's some random thing here that it didn't predict. Remember, this is still a noisy data set. And then when it jumps up, anomaly score again goes high, because it doesn't know anything about, of course, it didn't predict this transition, but even here, it's not predicting the step-by-step transitions, because it hasn't seen enough of that. But then over time, it's going to go down again. And again, every once in a while, some random event will occur, and you can see it picked up these two here with a high anomaly score. But then after that, even that is kind of expected, and so anomaly score will go down. Okay, yeah.
Okay, what if, say there's a jump in the data, but it's not necessarily a change in patterns. It's just a change in the level of the data. If the same patterns continue just at a higher level,
Yeah.
will anomaly scores stay high after the transition, or will it understand that it's the same pattern just at a higher level?
So it depends a little bit how you encode the data. If you just encode it normally like the way we do it, it's going to treat this as a completely new patterns. And so once it jumps up, it's going to start learning in this regime again. And that's the most flexible thing, because the chance that it's going to be exactly the same here is pretty low. Generally speaking, it's going to be different. You could have a differential encoder, so you don't encode the exact value, but encode the differences from one step to another. In that case, the anomaly score will jump up here, but then it'll say, okay, the differences are the same.
That sort of brings up a question.
Hold on, Jeff.
Regions.
Jeff.
Does this work with hierarchical regions? So, like if you had a melody, for example, or a sound wave, and it was very quiet, and then the volume went up, but the melody stayed the same, how would it react to that?
Yeah, so NuPIC today doesn't implement the hierarchy in the OPF, but in general, yeah, it will work exactly the same at every level of the hierarchy. And if you have multiple modalities, you could have an anomaly in one of the modalities and not in the other. So, if you have melody and volume, if they're encoded separately, you could actually detect the fact that it's the same in one area and actually changing in the other part. Okay, here's another example. This is the temperature of a heater in a office building, and you can see that this is just part of the data set, not the whole thing. You can see that there's sort of a regular behavior. It's a little hard to see here, but there's an unusual temporal behavior here, and the anomaly score here, generally jumped up. Here the temperature goes down and it became unusually low. In this case, the anomaly score again jumps up here. It hasn't seen, it sort of spikes low here, and the anomaly score spikes up there because it hasn't seen temperatures that low there. Okay. And I think I can't see exactly here, but there are some other anomalies when you actually look into zoom in some of these. There are some unusual things that it finds. Okay, here's one of the toughest cases. This is the random data I showed earlier. The anomaly score is much higher here than average, but it's kind of hard to tease it apart. So this is an example of where the current scheme, I'm not sure it really adds any value over the original data stream here. In fact, it's a little more bushy here. But I'll show you a little bit later how we deal with this kind of thing in Grok. But this is here where the data set is just inherently unpredictable. And so step-by-step anomaly score of the type we're doing in NuPIC doesn't really help you too much here. Okay, although you can visually see that it's different.
Just be clear, you're going to explain how we solve it.
I'm going to explain it,
Okay.
yeah.
Can I ask?
But in NuPIC today, if you were to, this is what you would get, and I'll explain exactly how we solve this problem.
Can I ask a quick question?
Yeah.
So, I mean, when you were talking about like web server latency, I mean, can't you just filter out the, can you just basically do like I guess it'd be like a short pass filter, a low frequency, basically filter out all the high frequency stuff and just look at the low frequency stuff, and then it'll make it a lot clearer what's going on.
Yeah. I think as a general comment, with any of these data sets, if you as a human were looking at it, you can craft something that will find that anomaly. You can definitely do that. As a data scientist or someone, you can come up with a mechanism to craft that. But the thing is, you don't know what it's going to be ahead of time. You want to build a system that's going to do well on a very wide range of data types. And as the number of sensors increases so dramatically, you can't be looking at each single one, seeing what the characteristics are, and then come up ahead of time with what the exact set of features, if you will, that's going to cap that. So I think you're right. I think for this, if we were going to capture this particular anomaly, you could definitely do that, but it probably wouldn't capture some of the other ones. No.
Yeah, but I mean, if you have a particular use case, you know what time scale is relevant, right? So if you know, like, you have a particular type of sensor,
Yeah.
you know which time scales are relevant, so you can optimize this in advance for that time scale that's appropriate for that sensor.
Yes,
right?
if you know a lot about that particular sensor and this domain, you can definitely do that. Yeah. Okay, so I put up some sample code in this in my GitHub repository. It's called Anomaly, and I put in some of the data sets that I've been showing you. And I put in a version of the HotGem anomaly script that Scott had created and made it so that it's easier to run multiple data sets and output the, look at the outputs and so on. So you could take a look at that, and these data sets are actually in there. So I think in NuPIC, we don't really have a great anomaly detection data set today. We're just using HotGem, which is not really an anomaly detection. There's nothing truly anomalous going on in there. But these data sets, there's something a little more interesting going on, so you can take a look at that. Okay, so let me switch topics and talk a little bit about Grok and how we have built Grok on top of NuPIC and how we solve some of the issues that we've seen. So quick kind of one-slide description of Grok if you haven't seen this. So Grok is the product that we put out that's built with NuPIC. And essentially what it does is it does anomaly detection for data from Amazon, data that's coming from Amazon instances. So Amazon has a CloudWatch service which is constantly monitoring all of your services, and there's a data feed that Grok can input from, and from there we will automatically put out, allow you to monitor all the metrics and then see what's unusual in your IT infrastructure at any point in time. Okay, and the nice thing about this is that it's completely automated. You don't have to tell it what time scale, or you don't have to tell it, whether it's load balancer or database data or anything like that. You just feed in, hundreds of streams of data. For each one, it does automatic anomaly detection, and then there's a really nice mobile interface, which we can show you later if you're interested, which sorts all of your metrics according to how, what is most unusual at any point in time. So even though you might have hundreds of machines, you can just very quickly and efficiently just look at what's unusual right now. So you can just focus on what's going on. We also have an API to feed in custom metrics. So you can feed in data that's not from CloudWatch, but your own data, and you can feed those in as well. And that's how I did the Lindsay Lohan thing, that I showed earlier. So you can feed in other data that's not CloudWatch data as well. So it's really kind of a general purpose. I wouldn't say general purpose, but it's a fairly flexible anomaly detection platform that you can use to try out some stuff. And because it's using NuPIC, it has all of the advantages of the CLA, and it continuously learns and adapts to changes. It deals with temporal anomalies and so on. Okay. So let me show you a couple of examples of what we can detect here. So this is essentially the same kind of data that I showed earlier. If you have a sudden change in your data, we can automatically detect that. Typically in an IT scenario, you would have to manually set thresholds and say, okay, if the CPU goes over a certain percentage, then raise an alarm, or if my memory usage is below a certain thing, then raise an alarm. With this, you don't have to set any thresholds. It's automatically kind of gauging the common spatial patterns, and then if there's a sequence or a pattern that's not what's seen before, it can flag it with a high anomaly score. Okay, so and I'm going to explain exactly how we compute this color here. But this is a simple case where we detect it, and as you can see, once it detects the jump, it will automatically adapt, and this is now the new normal. But at least you get an alarm when this happens. Here's another case where the CPU usage is extremely noisy, and it's sort of gradually drifting up. And after a while, when it gets beyond kind of the noise period, you see that the anomaly score goes way up because now it's finally, it's anomalous at this point. If you were to just look at this point, well, it could still be part of the noise, but once it's here, it's definitely anomalous, and you want to know about it. And this kind of thing is quite hard to catch, and often important to catch if you have a memory leak or some process leak or something like that. You want to be able to catch that kind of stuff. But it can also catch some pretty subtle changes. So here's an example of an instance, and let me just explain the display a little bit. This is one server that's it's monitoring, and these are different metrics that are associated with this server. So there's disk I/O, network input, and CPU, and it's detected an anomaly in the network bandwidth for this instance. And you can click on this and then see the data that actually led to this. And you can see it's this very bizarre, dense usage here. And there's an anomaly right in the middle here. The reason it's dense is that we're seeing 1 week of data here. So the data is sampled every 5 minutes, and we're seeing a full week's worth here. And you can see that there is these big spikes up that it does not catch as an anomaly. In this case, you can actually go back in time and see that these actually occur regularly. These are like regular cron jobs that do a backup or something at regular intervals. But it caught an anomaly somewhere in here. So you can actually drill in there and see what's going on. And what happened is that when you go to the daily level, you can see that there's a very regular, extremely regular pattern that happens very, very predictably. And at one point in time, that thing happened twice, and it caught that. So it's extremely unusual given how regular the pattern is. This particular thing is extremely unusual. If this had been very noisy, then this would not have been unusual and wouldn't catch it. But because it was so regular, it caught it. And quite often we find that when this kind of thing happens, it's usually one of our engineers has logged into the system and is doing something that's unusual for that server. So detecting these kind of behaviors is a really nice feature of Grok here. So how do we do this? Well, what have we learned in the process of using NuPIC for anomaly detection? Okay, so what have we learned from Grok? So first of all, again, anomaly detection is extremely useful. As I've been showing you, real-world data is really, really noisy. And it may be that for some of them, we can never build a perfect predictive model. It's just inherently noisy, inherently random. And you just have to deal with that. But still, humans can detect changes in that noisy behavior. So one of the things we learned is that you can't actually set a threshold on the anomaly score. And I think you saw that in some of the other examples. You can't just say, oh, if an anomaly score is 0.8 or higher, then it's, raise an alarm, because that would raise too many false positives. High anomaly score is not always bad. A lot of times just random stuff happens normally, and if you can't predict it, it's going to be a high anomaly score. So what do we do at that point? The interesting thing is that visually you can see a qualitative change in the anomaly score. So it is picking up on something, you just need to be able to pick up on that. And so what we decide to do in Grok is that we detect the change in the anomaly score itself. Okay? So what we do is we compute a probability model of the anomaly score. We see what are the average values of the anomaly score likely to be. We compute a model of that, and then given a new set of recent anomaly scores, see how likely it is that was actually predicted. So actually, let me just have a slide on that. So what we do is, for every new data point, we compute the anomaly score using the LPF, exactly like I showed you before. And then we estimate the probability distribution of the historical anomaly scores. So if you look at all the anomaly scores that have happened up to this point in time, what is the distribution of those? And we model it as a Gaussian today. And then, given that past probability distribution, we look at the recent anomaly scores and see how likely is it that previous distribution generated this recent anomaly scores. Okay, so we can compute a likelihood, a probability for that.
I just make it really clear, but not clear. We're looking at a recent distribution, like we look at multiple ones over the last hour.
Right. Right.
I know you said this, I'm not sure everyone will catch this, but so you can't do anything on a single anomaly score. You have to look at a recent average of anomaly scores compared to a longer historical average of anomaly scores.
Yeah. Yeah, so this is just kind of stressing that a single anomaly score, you cannot threshold or use a single anomaly score by itself when you have inherently noisy data. You look at the distribution of anomaly scores, and we are comparing the recent distribution against the long-term historical distribution. Okay, we're not doing it on the data; we're doing it on the anomaly score itself, and that trick actually helped tremendously in some of the data sets that I showed you. And I think in a practical system, you'll, at least with the state of NuPIC today, you'll have to do something like this. So let me give you a couple of examples. Here's an example of CPU usage. You can see that here's one type of behavior, and then it starts behaving differently, and then it spikes up again. And here's the raw anomaly score. Again, you can see it's definitely it's different here than elsewhere. But if you were just to do a threshold on the anomaly score, you'd pick up on a lot of extra stuff. But when you run it through the likelihood model, you can see that it really teases this apart. So here you can see that recent distribution of anomaly scores is extremely unlikely given the past distribution. So it very cleanly picks up this spike. But what's also interesting is that there are a couple of other places where it's also high. And you can see that it picked up on this square behavior here. So the right way I think to look at this is to say, suppose you're here at this point. Happen in the future. You're right here. You've seen this, and you see this square up. Is that an anomaly or not? And I think you'd say it is. And it manages to pick that up. It also picked up this little behavior here as anomalous. When it's changed from going, I don't know what, from this kind of behavior to this kind of more cyclical behavior, it picked up on that change, but then that's normal now, and it's fine, and then it picked up on this drastic change. Okay, so it's not perfect, but it really helps to kind of tease apart what we were able to see kind of visually in the anomaly scores before. Okay, is that clear? Yeah, go ahead.
So are you then advocating using a threshold for the likelihood score as distinct from the anomaly score, because you're trying to somehow encapsulate the human supervision or those visual cues that you would get by just looking at the score itself?
Yeah, exactly. So the question is, do we want a threshold and the likelihood score instead of the anomaly score? And that's exactly right. I think you can by thresholding here, you'll get far more informative notifications or alerts or whatever you want to do with the anomaly score with the system than if you just look at the anomaly score itself. And what's also kind of nice is you can actually put a probability measure on it. So you can say, notify me if there's a 1 in 1,000 chance of this happening. So you can kind of control the frequency of your notifications that way, naturally. Okay, here's the other example I showed you where you have extremely random data. And when you run it through Grok, you can see that the likelihood stuff picks up that regime very nicely. It picks it up as an anomaly, and you can kind of zoom in and see that it's able to do it actually pretty quickly as soon as these latencies start slowing down a lot more often. Let's see, this is the Windmill data that I had shown earlier, and you can actually run that through Grok, and you can see that it picks up the anomaly right where the wiggle starts to happen. This is, I think, a stretched out version of this. It's a little hard to see, but the point at where it picks it up is exactly where it starts wiggling more. Okay. Any questions about that? Okay, so the anomaly likelihood code. So the anomaly likelihood scheme has proven to be pretty critical in sort of converting where we are today with NuPIC into a practical application. And so we're actually making the code available. It's on that same GitHub account right now. I have a copy of the code there that you can take a look at. It's right now just a self-contained function. It takes in a list of anomaly scores and outputs a likelihood for them. I think it's might be useful to look at. I wouldn't say it's in a super easy to use form yet. It's in kind of the way we use it in Grok. But one of the things I think we could do is create better sample code around this and then maybe integrate it directly into the OPF. So the OPF itself is outputting not only just the anomaly score, but also the likelihood code. So then you can decide which one you want to use. Okay.
Jeff?
Yeah.
Is the likelihood code, is that based on the CLA, and are you running, basically are you looking for anomalies of anomalies? I mean, is it the same algorithm or is it a completely new algorithm?
Yeah, no, the algorithm for the likelihood is very simple. It's just fitting the anomaly scores to a Gaussian and then using that to compute the probability.
Okay.
But ultimately, it might be nice to see if you can do it in a hierarchy or compute anomaly of anomalies or anything. But
right, that's what his first
really
assumption
thought
was.
through
You
that
just
yet.
feed it back right
Yeah,
into
yeah.
the CLA. And
Yeah, because I mean, the brain is not doing the anomaly likelihood, but we're able to see these anomalies. So there's got to be eventually a better way to do it. Yeah. But I think in terms of building a practical product with today's code, this is a pretty good scheme, I think. But I wouldn't say it's the be-all and end-all of anything. Okay, so that's probably the biggest thing we've learned in building the practical system is that data sets are really noisy. You can't threshold the anomaly score, but building this kind of probabilistic model really helps you kind of tease apart where the changes actually are. And by the way, the simple stuff also works with this. So if you have a very regular data set and you have a anomaly in there and just a single anomaly score going up, well, that's also going to be caught by this, as you actually saw in one of the examples there. So the simple stuff is covered by this, as well as the more complex, noisy areas. Okay, so the second thing we learned is a little bit about swarming. So what about swarming? We talk a lot about swarming. So swarming is an automated parameter selection mechanism in NuPIC. So it basically allows you to run hundreds of models with many different permutations of the encoder parameters, the spatial pooler parameters, and so on, and it picks the best model and the best combination of fields that gives you the best predictability. So in swarming is actually, if you run it, it's a pretty time-consuming process, and it's really impractical to use it in a product if you want to get results very quickly. So what we do in Grok is we actually use a single pre-swarm parameter set. And we can do this because we have a very constrained kind of setup within Grok. So we have a very fixed set of fields. We have the timestamp and the metric value. We have data that's fed in every 5 minutes. And what we found is that the single pre-swarm parameter set works really well across different data sets, as long as they have kind of these two characteristics here. If you can fit it in here, it seems to work pretty well. You can still do better if you swarm, but the improvements is incrementally pretty small. So this was a really huge step. One of our interns actually figured this out last year, and it just made a whole bunch of problems go away when in doing a production system. So at least within this constraint set, you can use a single pre-swarm parameter set. I think in general, you will still need to swarm or do some sort of model selection. I think there's a great set of tutorials online put together by Matt, and there's lots of people here who can help you. If your data can't fit into this format, you'll probably want to do some swarming. But the good thing is, what this really taught us is that the system is pretty insensitive to small parameter changes. If the structure of your system of your problem is not changing much, then you may not need to swarm too often. You can swarm, once or twice and just use that model parameter. So this was a really nice kind of learning that we had last year.
Yeah, I'm just going to add something on top of that. The comment on the second bullet up there, which says fixed set of fields, was interesting. This intern who did this determined this by looking at data that was unrelated to what Grok looks at. And so I want to make it clear that the pre-swarmed model is not pre-swarmed on the data we actually use in Grok for servers.
Right.
It basically seems to be independent what the data represents. So what the point of this is that if you have a single metric plus a timestamp every 5 minutes, it should work. That's been our observation so far. It doesn't have to be pre-swarmed on your data.
Right.
It's not specific to the data. So we feed in data into Grok that goes between 0 and 100 for like CPU utilization, between 0 and 600 million for, I don't know, whatever that is, network index or something like that. And the patterns look all completely different. So really, I just want to make it clear that It's just the number of fields that matters. It might even work with 2 or 3 fields. We don't know, but all it says is if you have a single field of data and a timestamp every 5 minutes, it doesn't really matter what it is. It seems to work well.
Yeah, and you could see that with the Windmill data that I passed in. I worked on that. It was never swarmed on that. It wasn't swarmed on the IT data. I didn't know anything about Lindsay Lohan or anything. But it, as long as it fits into this format, it seems to work pretty well. And and that might be important. If you for the hackathon, if you think about anomaly detection and projects, if you can fit it into this format, you can just avoid swarming. You can use the parameter set that we have today. Okay, so that's Grok. And so, where do we go next? I think we've seen that the CLA is proving to be really good at detecting anomalies in a large range of data sets that we've tried so far. And within the context of Grok, it's fully automated. There's no parameter tuning whatsoever. We've learned a lot in the process of creating the product, and I think, with talks like this, I think we want to spread the ideas out into the NuPIC community as we learn more, and hopefully others will do the same thing. So as a community, we can get better and better at this process. But at the same time, it's clear, I think we're just scratching the surface. There's so many other types of data and multivariate anomalies and all sorts of stuff that we haven't really started to capture, let alone, you might want to do anomaly detection on text streams, using the CEPT API or some, there's anomaly detection, I think, again, is a very fundamental capability. So I think we've just started scratching the surface of this. So I think that we still have a long ways to go. One of the things that we're just starting to do, I mentioned earlier on that it's really hard to find good data sets that cover the full span of things that we want to look at. So what we've decided to, here it says hard. What we decided to do is actually create a benchmark data set and a testing methodology that's focused on streaming data and anomaly detection. So what we want to do is create a benchmark that models real-time online continuous streaming data sources and with an emphasis on temporal data, automation, continuous learning, all the things that we've talked about so far. And along with a well-defined methodology for evaluating these algorithms and maybe some baseline results with the current state of CLA. And we're hoping that by creating this data set, that'll help us again in improving the technology down the road. And we can expand on this data set over time as we find new categories or new types of data that we might want to do anomaly detection on. So this is something that we're just getting started on. We're hoping it'll be useful to the NuPIC community as well, and hoping you guys can contribute to it as well. Please see Ian Danforth, who actually stepped out for a couple hours, but he'll be back again. He's the main person putting this together for us, or see me or any one of us if you're interested in kind of contributing to this. Okay, and then last slide, a couple of resources. Jeff wrote a white paper, The Science of Anomaly Detection, which is on our website, which covers a lot of the topics I spoke about, so you should definitely download and read that. There's the GitHub repository again, and here's a kind of a random thing. If you're interested in other machine learning techniques for anomaly detection, this is a pretty nice survey of that. It's a pretty big paper, but if you're interested in that, take a look at that. I think it's useful to read through it sometimes. So. Okay, thank you. Any questions?
Hi, Subutai. Just one question. You can generate an SDR of the anomaly scoring columns, is that correct?
You mean which columns led to the anomaly score? Yeah, you can compute that. That's, I think, done in CLA model.py. Actually, Scott, I think, moved it. There's a function in algorithms, anomaly.py or something that computes that.
Yeah, you can find that it comes out of the TP. And
exactly.
You can extract an SDR, because we are working on using the CEP stuff to do the thing on these Libya tweets.
Yes.
So we want to generate an SDR of the anomalous columns.
Yep.
Give that to CEPT and find out what word is causing the anomaly.
Ah, okay.
Yeah.
Okay. Yeah, cool.
Any other questions?
Just a quick, I'm wondering, you've never turned learning off for when you run your models or when you run your Grok systems. So it learns the anomalies.
Yeah, that's right. So the question is, we don't turn learning off at all. So, wouldn't it learn the anomalies? And it does. And, so if a particular pattern happens more than a couple of times, it's not going to be flagged as an anomaly. And so there's actually, in most cases, that's what you want. Like you saw in that step up function, you don't want to keep giving alarms continuously. That's one of the biggest problems the IT people have today with the existing anomaly stuff, is they just get way too many alerts in those situations. So it'll give an alert when the anomaly happens, and if that's the new normal, it'll kind of, it'll learn that and won't be an anomaly. If you want, there's actually a mechanism in NuPIC to store the pattern that caused the anomaly, similar to what Fergal was just saying. And you can store that in a classifier, and if you want to, you can try to detect that again if it happens. So that's kind of a separate mechanism. It might be that there are some specific situations that do occur, repeatedly, and you do want to detect them specifically. So you can store those in a classifier and detect those.
Okay, thanks.